So in yesterday's discussion, we had talked about the testing hypothesis, right? How is it that you frame a conjecture? What exactly is a null hypothesis? What exactly is an alternate hypothesis? What is the level of significance? What is a p-value? And how is it that we use these p-value and the level of significance in creating these, in taking up the decisions, right? And one very important concept which we have come across already is the concept of observed differences versus significant differences. Right. So in yesterday's discussion, we came across the fact that how do we take the decision that what would be the rejection. I mean, what would be the outcome if the p-value is less than alpha? What would be the outcome if the p-value is greater than alpha, and so on, right? So each of these cases, we saw how is it that the observed difference and the significant differences can be. So coming up from this part, we decided that we would be exploring different kinds of statistical tests, right? And in that process, we will be coming across some important statistics. And one of the tests with which we begin our discussions over here is the t-test. Is the t-test. And when we talk about t-test, we will be talking about some important variations of the t-test. One of them being the one sample t-test, the other being the two sample t-test. Also, whatever the next being the next part, which is the for the multiple sample mean difference test and so on. So what we need to understand is primarily the business areas where, or the areas relevant to model development, where these concepts of tests and F tests would be required, right? So over here, what we have is, so we start off with single mean test, or the case where we are trying to assess whether, or we are trying to conjecture whether the mean is of a particular value or not. So that is where we talk about the single mean test. So in this case, you can think about that you have a sample mean, right? So you have a sampling distribution, from there you have computed a sampling mean, and hence a population mean by computing the expected values of the X bars. So let that value which you have computed, that expectation of X bar, be a value equals to mu naught. So what is basically this mu naught? Mu naught is the expected value of X bar which we have computed from the basic sample distribution. Now what I want to know is, that can I use this value and say that this is nothing but the population mean. Now what would happen? So what I need to do is I need to do a test. So what is my test over here? My test over here is that H naught is mu equals to mu 0, mu 0 versus HA mu not equals to mu 0. Mu not equals to mu 0. Now when I say this, right, so what is it that I mean by this? So what I mean by this is the following. One of my conjecture over here is that the mu 0 that I have obtained from my calculations or from my model, whatever you see, from my estimation, that may or may not have some difference with the population between. But the question that comes out over here is that does this mean that there is, or the difference that I can see between mu and mu 0 is significant? So basically, I consider the difference of worth a difference if the difference is a significant difference. However, there might be certain observable difference or observed difference between mu and mu 0. Now my objective is, so my conjecture is both. My now conjecture is that mu must be equal to mu 0. Whereas my alternate conjecture is that no, there exists a significant difference between mu and mu 0. Hence, what I can clearly suggest over here is that this mu is not equal to mu 0. The mu not equal to mu 0 is, mu not equal to mu 0 will hold if and only if the difference is significant. Now, how do I assess if the difference is significant? So, for that, what I need to do is I need a test statistic, right? And to do this kind of a mean test, the single mean test, the test statistic that we use is called the t-statistic. This is also known as the student's t-statistic, right? So we use the t-statistic. So what is the t-statistic all about over here? So the t-statistic is nothing but t-statistic says the difference between mu 0, mu. So it helps me calculate the difference between mu 0 and mu relative to the overall variations in the dataset, which is the standard error of this X bar series. So over here I have computed an X bar, expectation of X bar. So also corresponding to that I will also obtain a standard error of X bar, right? Error of X bar. Now compare, the next thing is you compare this with the critical value of t. Now how is the critical value of t defined? The critical value of t is defined with respect to a level of significance. So what it says is that assuming that we allow for 5% chances of committing the type 1 error, the minimum distance between mu naught and mu relative to standard error of X bar should be this value, such that for the difference to be called significant, right? So, like in this example that we had, when we had coined this particular example of 40, right? So, when we considered this cutoff value of 40, we had assumed that there would be a permissible error of 60%. So over here, what we are creating is, what we can say from here is that assuming that there is a 5% chance of committing the type 1 error, right? I require the difference to be minimum of this value t critical. So the t critical shows the minimum amount of distance between mu0 and mu that must be, assuming that there is a 5% chance that this distance would be an insignificant distance, right? So at that minimum distance there would be a 5% chance of committing a type 1 error. So that is the critical. So basically if the actual statistic is greater than the critical difference, what it means is that the actual probability of committing the type 1 error P will be less than the critical level of the maximum permissible error. Just to understand this, so over here the marks that we had over here was 100, full marks was 100, right? Now the school authorities had assumed that there was a maximum permissible error of 60%. So assuming that the maximum possible error that the student can commit is 60%, the cutoff was put at 40. However, however, when a student gets 25, then we can say that the actual value of the statistic or the actual marks obtained by the student is lower than the critical value, right? So in that case, what happens is T is less than T critical. If T is less than T critical, that means that the distance which T has suggested between mu and mu zero, if I consider the difference to be significant, then there is always a greater chance of committing a type 1 error. So when the student got 25 over here, the actual error he committed was 75%, but the maximum permissible error was 60%. So what we saw over there was that when T is less than T critical, then it vis-a-vis would imply that P, the P value is greater than the alpha. So that means the actual chances of committing the type 1 error are much higher than the benchmark chances of committing the type 1 error, right? Now if that is done, then the next thing that we try to look into is that with P greater than alpha, right, H0 will be accepted, because if the actual chances of committing the type 1 error is greater than the critical the maximum permissible error, then my model actually runs a greater risk of committing the type 1 error. Hence, it would be better for me to choose the null hypothesis. So, I would not take the risk of rejecting the null. Instead, I'll accept the null. Right? So, if P is greater than alpha, then H naught is accepted at alpha level of significance. Clear? H naught is accepted at. So what does the alpha level of significance talk about? The alpha level of significance is kind of a benchmark of a good test. So basically, I consider my test to be a good test if out of 100 trials, right, I do 100 times, I estimate this 100 times on this testing procedure, right. Out of that, there's only 5 times when I end up committing a type 1 error, but other times I am not committing the type 1 error. Therefore, that is what is the alpha level of significance. It specifies a cutoff or a benchmark for a good test, right? So this is how the basic test procedure is executed. So this is a single mean test where we are trying to test whether a particular mean is equal to a population parameter mean or not, right? So this is what the single mean test is all about. Now after this, the next part is the mean difference test. Now, the application of this mean difference test is widely spread all across the part of all across the modeling exercise. Not only in the part of the modeling exercise, but also in a lot of different areas, right? In retail, in so you are in assigning in segmentation purposes, everything. So there are a lot of areas where this mean difference test can play an important role, right? So this is something that we discuss next. So just go through this, whether this p greater than alpha and whether this testing rule is clear or not. Just go through this for a minute, then we'll start. So coming to the part of mean differences. Now the question of mean difference test arises when there are two or more groups of observations and you want to assess the difference in the mean between them. Now, now why is this or what is this part all about? So what we can say over here is the following. That say let's take the case that there are two pizza companies, right? So there is Domino's and that there is Pizza Hut. Now what they do is so they run the outlets one on a side by side basis, and they are delivering the pizzas. But it is seen that despite Pizza Hut is a better pizza brand, but still the sale of pizza is actually falling down. So now, what they do is the HR team, I mean the management and the analysts, they do a deep drill down, right? And once they do a drill down, what they do over there is, or when they drill that down, when they do a drill down, they see that the average delivery time, right, of Pizza Hut has turned out to be greater than that of Domino's. So there is a basic difference. Right. Say suppose Domino's delivers a pizza in 10 minutes, but Pizza Hut is delivering it in 11 minutes. Now the question that comes out is that I can see that on an average the difference is So there exists a difference between the two. But what the people want to know is, but what the analyst or what the manager knows is that is this a very significant difference in the average delivery time. So they are delivering it in around 10 minutes, some seconds, and we are delivering it in around 11 minutes, some seconds. So is that difference of 1.5 minute a lot? I mean, is that a very large difference that is there? So so how do we work that around? So if there is if there exists a difference like this, then how is it that we can take care of that, or is this difference a significant difference or not? So that is where the statistical testing or the mean difference t-test comes into play, right? So suppose I see that there are two assets which give more or less similar returns, but the return of asset A is greater than the return of asset B. The question that I ask myself is that is it that the difference in A, I mean, difference in asset, the return of asset A is greater than the return of asset B. So how does that actually work out? So this is where the next part of the story comes in, and this is where the mean difference, the story of the mean difference t-test also comes. So how do we do the mean difference t-test? What are the hypotheses? So the hypothesis of mean difference t-test is as follows. It states that H0 is mu1 minus mu2 is equal to 0 versus the alternate hypothesis mu1 minus mu2 is not equal to 0. So this is what my testing conjecture is. So over here in the first case, what I'm saying is that I can see some difference exists between the two mean values, but is it that, I mean, but the difference between the two mean is not very significant, right? Versus the alternate hypothesis is that the difference between the two mean is extremely significant, right? So this is what the testing hypothesis or the test hypothesis is. So if I test that the average delivery time, so when I look at the average delivery time and I see that average delivery in that average delivery time, I mean the difference in the average delivery time, the difference is not very significant, right? So the idea that comes out over here is that how is it that we are going to test that? So if the difference is not very significant, then as a pizza company, I am not really bothered about that. However, if the difference is significant, then we need to design strategies to streamline down the time period over which I am actually working. So what should be the T statistic like? The T statistic over here should be, say, suppose the mean of the two groups are mu1, right? Minus mu0, sorry, it's not mu1 minus mu0, it's is mu1 minus mu2 minus the expected value of mu1 minus mu2. Right, and then what we have over here is standard error of mu1 minus. So this is what the p statistic is, right? So over here, what we want to know is that what exactly is, how significant is this difference between mu1 and mu2. But so again, I mean, as far as the decisioning formula is concerned, the decisioning formula is absolutely okay. And what you have is, like if p is less than alpha, that is, if the p value is less than the level of significance, then H0 is rejected at alpha level of significance, else H0 is accepted. So that is all right, right? Now the question that comes out over here to me is the following: that uh, what do you think? So basically, I have this test hypothesis. I do this test, right? And I take my decision out. So, but do you think in between this, something else should have been checked before directly testing the difference of the mean? So, is there something that we should have checked, we should have analyzed, and then we should have created this test statistic, and then whatever the blah 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 the decisions are. So before reaching out to the point of p less than alpha, right? Do you think that there is something else that we should have checked, which we have not done over here as of now? Yes, so you are computing or you are comparing the difference in the means of two groups, right? So what else should you check? Parametric. So as in parametric, as in what, Anirudh? Sample size, okay. Anything else? Right, variance. Absolutely correct, Anirudh. So basically, the idea over here is that you should have checked the variance between the two data sets. So basically, if I'm comparing the mean, right? So there is, say, group A and there is group B, right? So let's think about the case that Pizza Hut uh, delivers a pizza at around at 11 on an average time of 11 minutes. So some pizzas go out at 10, some pizzas go out at 9, right? So over here, what we get to see is that this continues and this thing actually keeps on moving, and this keeps on like going ahead. So and most of their values are delivery times are like distributed between 9 to 12, 9 minutes to 12 minutes, right? And the average is around 11. Now Domino's on the other hand delivers one pizza say at 3 minutes time, but the next at 23 minutes time, or say one is delivered as 5 minutes and the next delivered is within 25 minutes, right? Or say 20 minutes or 15 minutes, like this. So the variance, if you are trying to assess whether there is a significant difference in the mean or not, then the overall variance in the two data sets must be more or less similar. So whatever variances that they have, we should actually test whether the variances are significant or not. So that is where we need to do a variance check. So we need to check whether, so before performing this test, it has to be checked, or it is generally checked. I mean, as it's by default it's done. You need to check whether the two population variances are more or less similar or not. So one of the tests over here would be whether 80 sigma 2 square. Now we cannot actually say that the variance must be equal. What we need to say is that there must not be any significant difference between the two variances. So whatever differences can be observed is because of sampling fluctuations, nothing else. So whatever differences are there, those differences should not be anything significant in nature, right? So this is where we have HA. So the HA over here is sigma 1 square not equals to sigma 2 square. Right? So over here sigma 1 square, so we need to do this variance check, and we need to ensure that the variances in the two different data sets are equal. So there is not much of significant difference between them. Right. Now having said that, the question that comes out is how do we do that? So this test is done using a test called the folded F test. And the folded F statistic is a very interesting statistic. It's a very simple but an interesting statistic. So over here what it says is the folded F test, the folded F statistic is equal to max S1 square S2 square. So so what we talk about is the folded F, right? So so this is defined as the difference between the maximum of the two sample variances and the minimum of the two sample variances. So it is the folded F statistic is a ratio between the max and the minimum value of S1 square and S2 square. Right. So first, the folder def test is actually used, and it is identified whether the data, the folder def test is used, and it is identified whether the max and the mean ratio is there. So once this f folder def is obtained, then it is checked whether the null hypothesis is accepted or rejected. Only if the null hypothesis is accepted, that is sigma 1 square and sigma 2 square, that is no very significant difference in the variations observed between the two population, only then this test would make some sense, right? So once the folded test is done, then we go into do this mean difference test, right? So which is done using the t-test. Now when we have completed, or when we have discussed this, when we talk about this mean difference test and this t-test and all, so what do you think should be the basic characteristics of a t-test? The first and the most important characteristic that t-test has is of normality. So t-test is primarily a parametric test, as it is based on the assumptions of normality, right? So it is assumed that the distribution of the variable is normal. Distribution of the variable for which you are doing the test, that variable is normally distributed. Once you have identified that it is normally distributed and all, then the next part that we talk about is that there is like, you know, so this there is this null hypothesis and this alternate hypothesis. So basically, once you identify that it is normal, the next thing that we do is we test whether between the two groups the variances are more or less homogeneous or not. After that, the t-test is, or the mean difference t-test is executed. Therefore, this t-test that we are talking about over here is, as Anirudh sometimes uh, back referred to it, that test is a parametric test. Well, it's a parametric test because it relies, or it begins with the assumption that the variable must be normally distributed. Right. So this is what the overall idea is. Right. Now the question that next comes up. So is this process of doing the mean difference t-test clear to us? Any questions on doing the mean difference t-test? Great. Now the question that comes out over here is that where is it, or what is a domain, right, where we apply this test? So this is what we need to understand. Now, one very important part where t-test is used is variable selection. A t-test can be used is the variable selection point. So, for example, just suppose if I have a risk scorecard, right, and I want to decide on a variable, whether a particular variable should be selected in a model or not. That is where this variable is, so this concept is used. So over here, what we have is the variable selection, right? So, what is a variable selection? So, when we are developing a model, right, we need variables for that. So, we require some variables which could help us explain the dependent variables in the model. Now, just selecting a variable like this cannot be, uh, I just cannot randomly take up variables. I need to have variables which, I need to have variables which can distinguish between the good and the bad, right? So variables which can distinguish between good and bad borrowers, and that is where the concept of variable selection actually comes in. So variables, say suppose I'm trying to develop a application scorecard. So just before I move into this describing what this test teaming difference test is, just let me give a just let me give a brief idea about what application scorecard is. So okay, so by any chance, do you know what an application scorecard is? Any idea? Any idea what's an application scorecard? A brief idea. I don't want a very exhaustive idea. Okay, a decision making model to grant or not to grant a credit. Great. So over here, so basically, now let's think about it like this. So there is a model. So there is basically a borrower who is coming up to the bank asking for a credit. Now it is the biggest problem of the bank to decide whether to whom to give the credit and whom not to give the credit. Right? So this is where the entire problem begins, and this is where your application scorecards become really very important. Right? Application scorecards are actually very useful techniques for model development. For risk management at the origination stage. So what happens in the origination stage is the following. So at the origination stage, the borrower applies for a credit. Right. Now the bank tries to assess whether this borrower is a good borrower, is a good borrower or a bad borrower. Therefore, what the problem or the business problem that the bank or the risk managers try to answer is the following: that y equals to 1 if the borrower is a good borrower. If good. Equal to 0 otherwise. So over here y equals to 1 if good, equals to 0 otherwise. Right, so this is what the first condition is. This is what the first criteria is. Now having said this dependent variable, right, the next thing that we need to do over here is we need to, so as this managers, what do I want to do, or what do I need to do? What I need to do is I need to estimate the chance that the probability of y equals to 1, chance of that the borrower is a good borrower. So that is the probability of y equals to 1. Right? Now, if I am trying to estimate the probability of y equals to 1, I have to do it a basis a such set of certain factors, and that is called the variables. Variables. So now, say suppose I start off with a set of, So there were 1,000 variables when I had started it. But I cannot use all these 1,000 variables to develop my model. So from here, I need to choose the four or five most predictive variables. So I need to identify those variables which are the best possible distinguisher between the good and the bad. So those variables will actually enter into my model. So like out of all these 1,000 variables, like four or five variables will enter into my model. Four or five variables will enter into the right. Now, if we have these four or five variables, that means there must be a mechanism of selecting these four or five variables from the entire list of 1,000 variables. So the question that comes out over here is that how is it that this is being done? So over here, what we have is the following. So this part, so choosing the four or five out of 1,000 is a part of your variable selection. Now, when should I choose a particular variable for developing a given model? What do you think? The variable selection. So there is a variable selection, right? So when what do you think? So what should I keep in mind when I'm selecting variables? Say suppose out of 1,000 variables, I give you a variable x1. Now my question is that should I choose the variable x1 or not? Yes. So why? So if I am given a variable x1, right? So why do you think I should choose, or rather, when do you think I should choose x1? What are the characteristics that x1 should satisfy for me to choose x1 as an independent variable? When should I choose x1?
When X1 has strongest predictive
Correct.
power.
Correct. So rather than predictive part, what we should think about it, its most informative capacity, right? So when I say x1 is the most predictive variable, what I mean is that it has the greatest informative capacity. So x1 will obviously, or any variable would be chosen basis on its information value or its informative worth. Information worth. Now, when I talk about this information worth, the next part that we try to talk about is, so when I talk about information worth, right? So what is this information worth? Or how would I assess the information worth of a variable x1 for this particular case? I would say that this variable x1 has a very high information worth if it can distinguish between the good and the bad distinctly. So if this variable has the capacity to distinguish between good and bad, then I will say that yes, this variable is an important variable. So, so it means, So when I say that this can distinguish between good and bad, what I mean is that historically, for this variable, the average behavior of this variable for good borrowers has been significantly different from the average behavior of the bad borrowers. So, in other words, what I can say is that the average variable, the average behavior of x1 for the good borrowers was significantly different from the average behavior of the bad borrowers. So therefore, if the variable x1 can distinguish clearly between the good borrower and the bad borrower, then I'll include the variable. What it means is that if the average behavior of x1 across the good borrowers and the average behavior of x1 across the bad borrowers is significantly different, then I'll consider that this variable can enter into the model development process. So this is one area where mean difference tests can be used. So basically what I need to test is whether the average behavior of x1 across the good borrowers and the average behavior of x1 across the bad borrowers, whether this is significantly different or not. So average behavior means the average. I'll give you an example. Say for example, there is a healthcare financing portfolio, or right. So in healthcare financing portfolio, as in a diagnostic firm, right? And they approach a bank. Say they approach HSBC, or they approach Citibank for model. So for a working capital service loan, for some working capital services. So basically, what is this working capital services? So for working capital services, it is like the bank, these healthcare organizations, diagnostic firms, they require huge amount of working capital on a day-to-day basis. Right? Like they require cotton, they require medicines, they require capsules and stuff like that, right? On a day-to-day basis, they need funds to maintain their working capital on a day-to-day basis, right? So therefore this working capital that we have over here, the working capital services that we're talking about over here for banks, right? They finance the working capital of different firms. So in this case, the example that I'm giving you is of a diagnostic firm, of a healthcare financing unit. So what the bank does is the bank under their healthcare financing services portfolio, they give working capital services, provide working capital services, and they give out the loan, and they are deciding whether to give out a loan to the diagnostic firm that has approached them. Right now, one of the important variables. So whenever you are lending to commercial borrowers, one very important metric always is EBITDA. That is the earnings before interest. Earnings before interest, tax, depreciation, and amortization. So there is this EBITDA. Now, when the modeler was developing the model, right, so he wanted to assess whether EBITDA should enter into the model as an explanatory variable. Now, why is EBITDA being constant? So, what exactly is EBITDA? EBITDA is nothing but is the earning. It gives us an idea about the profitability of the business of the firm, right? So it tells us that how profitable is the firm, how profitable is the company that we are working for. So this working capital. So therefore, EBITDA should ideally give us a very clear idea about the performance of the company. So basically, now if I think about it, the relatively risky borrowers, the relatively bad borrowers will be the one who are not performing properly, right? They should be the one who are not actually performing properly, and hence their EBITDA should be relatively lower. On the other hand, for the good borrowers, the EBITDA should be relatively high. And it is this part that this distinction comes. It is this part that we question ourselves that if EBITDA is to be a good borrower, I mean, if EBITDA is to be a kind of a good indicator, I mean, it is to be a good variable, then it should be in a place, it should be in a position to distinguish between the good and the bad. That is, the average EBITDA for the good borrowers should ideally be higher than the average EBITDA of the bad borrowers, right? So if the average borrower has, say, there's a, so the bad borrowers would be performing relatively low in terms of EBITDA, right? Because their financial statement would be relatively worse off, and hence they are relatively more risky borrowers. On the other hand, the good borrowers should ideally have a relatively higher value of the EBITDA. Therefore, when I'm talking about this working capital services, right, when I'm talking about the working capital services, then EBITDA becomes the variable, and I would incorporate it into the model only if and only if the EBITDA for the good borrowers, right, the average EBITDA, the average EBITDA for the good borrowers is strictly greater than average EBITDA for the bad borrowers. Average EBITDA for the bad borrowers. Right. So over here, what we have is working capital EBITDA, right? So over there, what we have is two groups: good borrowers and the bad borrowers. Now, if EBITDA actually has the capacity to distinguish between good and the bad borrowers, then when will it happen? If we see historically that the average behavior or the average EBITDA earned by the good borrowers are higher than the average EBITDA earned by the bad borrowers, then we know that the average, we can say that the EBITDA has the capacity to distinguish between the good and the bad borrowers, because the average behavior of EBITDA for the good borrowers is strictly more than the average behavior of EBITDA for the bad borrowers. Right, so that is where, and if then this should have a sufficient significant difference in the mean between the two groups, then there must be a significant difference between the mean of the two groups. So that is how, so this is one place where this industry is, so this is one place where this t-test kind of an approach can be used in statistical analysis in the part of quantum risk model development. Right. So is it now clear that how this concept of mean difference test is coming in? So basically over here what we'll have is a 0 mu good minus mu bad. 0 mu good minus mu bad is not equal to 0. Kumar has a question over here. That EBITDA might vary with the revenue of the company. So should we take average EBITDA as a variable? Yes, you can take average EBITDA as a variable also. Average EBITDA over time. Or you can also take, say, percentage change in the average EBITDA over the last 3 years. Or you can also create some other variables that number of months for which EBITDA has successively gone down by so and so percentage over the last 12 months. So you can create multiple variables about EBITDA, but the base variable remains EBITDA, right? Okay, great. So this is one way where one part where this EBITDA, I mean difference test can be applied. This can be applied. The third thing, another area where the test can be applied is for segmentation purposes to some extent. Say suppose I'm creating two segments, right? I've created two segments. Now I want to know whether the segments are properly or have been created or not, or whether the segmentation is proper or not. Now the question that comes out is that why do I create segments? Why is segmentation done? Segmentation is done in order to identify homogeneous groups of populations. What I want to identify through what I want to identify through segmentation is homogeneous groups of loans, right? So in a risk data, right, there are different categories, there are different types of borrowers constituted together. Therefore, a lot of multiple risk tendencies come and cancel out, and they create a very heterogeneous kind of an entity there. So what we need to do is we need to disentangle these different kind of these tendencies, and that is where the role of segmentation comes in. Right? So if there are two segments, segment A and segment B created, then it is very important to test whether the pad rates across the two products, I mean across the two segments, are significantly different or not. Right? So there are different kinds of business driven segments which are identified, and then they are tested whether these models are, then it is tested whether the two segments differ significantly in terms of their riskiness or not. So basically, if I have created two segments, segment A and segment B, then either segment A is more risky than segment B, or segment B is more risky than segment A, or segment A, right? But they cannot be of similar riskiness. If they have similar riskiness, then they need to be punched into one single segment, right? So therefore, what we need to do is we need to test the differences, the significant differences in the bad rates, or the bad rates are nothing but the average rate of defaults across different points of time. So again, that leaves a scope for performing difference tests in the domain of banking analytics, right? So basically, if segmentation purpose, segmentation is a very important area where this mean difference test can be applied, right? Okay. So the average rate of default means I'll just come to what average rate of default means. Okay. So just give me a couple of minutes. I'll just be back and we'll get started. Hey, hi guys.